Okay. Is that no? Right. Now have I got everyone? Yep. Where's David? Oh, there you are. You're on this side of the room. That's messing with me. Sabrina. Where's Priscilla? Oh, there. Okay. Patrick. Vanessa. Oh, there we go. Umar? Oh.
It's for the year.
Ishpreet. Oh, so I have everybody. Great. Okay, let's get started. Now, what we're having a look at in the first class is a thing called Venn diagrams. Now, this isn't very difficult, and the reason we need to study this is because it gets used in probability. Because I think we have a little bit more probability to do, but not much. But we kind of need to have Venn diagrams covered. So,
What page is it?
94. You all know what a set is, don't you? Yeah. What would you say the definition is? Little bit more than that. It's not quite to do with probability just yet. Not just yet.
It contains the. Okay, fine.
Why?
Anyone know? Yeah, it's a collection of elements that follow a well-defined rule. So what I mean here is your set, it has to be clear what's in it and what's not in it. Okay, so for example, here's set A. I could say it's the set of all even natural numbers. That would be a very clear set. So the way we represent sets, as you know, is with these curly braces. So that's 2, 4, 6, etc. Like that. Okay, so that would be an example of a well-defined set. B, another example. You could say something like, students in this class. So the list of students in this class would be a set as well. An example of something which is not a good set. So this one would be, this one's good, and this one's good, and this one's bad. This would be the set of older students in this class. Now, why is that not a set? What's the problem with this? It's not well defined. It's not clear. Okay, so we can write that a little bit down. There's some basics of sets here.
Rule.
That follow a well-defined rule. Okay, have you got that? No. Got that? Well, can I just scroll down a little bit to here, yeah? Okay. So, some notation which, again, I hope you're familiar with. If I write this, what does that mean? X is an element of A. So, meaning basically that X is one of the members of the collection that's set A. And then I think it's fairly obvious what this means. X is not an element of A. Okay? Yeah? Yeah? Okay, a little bit more, well, actually, just, yeah, a couple of more things about sets. So this here, also written like this, is called the null, or empty set. It has no members. There is nothing inside of this set. So no matter what element I pick, I automatically know it cannot belong to the empty set. Yeah? Empty set doesn't contain anything. Okay?
Null is the same as empty set, yeah?
Yeah, the same meaning, yeah. So you have to be careful a little bit about sets. So if I have the set 1, 2, 3, is that, or is it not, the same as the set 2, 1, 3? It's the same, yeah. Because a set is only a collection of elements, but we don't care about the order at all. And what about the same or different? No, still the same. Still the same. Because if I said to you, is 1 an element of this set? That's yes. 2? Yes. 3? Yes. Anything else an element of it? No. That's the exact same statements I can make about this set. 1's an element, 2's an element, 3's an element, and nothing else. This one here? These are all the same. These are all the same. Oh, because it was a question. Is it equal or not equal? So, it was equal. These are all equal. They're all the same. Yeah?
Because it's a collection,
Yeah, or really it's like a list of what's in and what's out. So it doesn't really matter if you duplicate. Yeah?
Because it's this topic, I don't know math. Because I'm listed, and then like every time I say something.
Okay, you got that? Yeah? So, this symbol here, or this symbol, well, they're different, but they're very similar. This symbol here, do we know what these are called?
Subset.
Yeah, this is a subset, and this is a subset. But the one on the left has a slightly different name. No, it's still a subset. This one's called a proper subset. Firstly, what is a subset? So a subset is a relationship between sets. If I say A is a subset of B, that means for all X that's in A, it's also in B. So everything that's in A is also in B. Okay?
Say that all X is set in B also.
No, B could be bigger. So all we need is everything that's in A is also in B, but perhaps more. And also, A A and B are different.
One. Oh.
No, no.
A will be
I haven't said anything that needs a question. I'm only giving you a definition.
What one?
Why am I giving you a definition? Can someone answer that for me, please?
Probably
Why?
getting money for this.
Why might? Yes. I'm getting paid to teach you and give you definitions. Yes. I'm confused. I'm not doing anything that should have a question.
No, why they're not equal?
But that's part of the definition. That's what it means to say A is a subset of B.
47.
Yeah? You're confused. No, I'll give you an example to make it clearer. I'll give you an example. Guys, look up. Here's an example. Here is set A. Let's say 1, 2, 3. And here is set B. 1, 2, 3, 4. Are A and B the same? No. But is everything that's in A also in B? Yeah. Yep. So we have A is a proper subset of B. So what's the difference between this and this symbol? Not much. The other symbol, here A is a subset of B. This has a very similar meaning. It means for all x in A, we also have x in B. But I'm dropping the requirement that A and B have to be different. So it's possible that A could equal B, or not. It doesn't matter. So I'll give you some examples of this one, okay? Let's say A equals 1, 2, 3, and B equals 1, 2, 3, 4. I can still say this. A is a subset of B. Now, if I had A equals 1, 2, 3, and B equals 1, 2, 3, again, I can still say this. I've removed the restriction that A and B have to be different. Whereas in this one here, if I had A equals 1, 2, 3 and B equals 1, 2, 3, could I say A is a subset of B using this symbol? No, because in this definition, A and B have to be different.
Is the second one?
Yeah. In other words, the difference is a lot like the difference between this and this. Here I'm saying x is less than y, and here I'm saying x is less than y. In the first case, though, is it allowed that x could equal y? No. But in the second case? Yeah. That's exactly the same type of difference between these two symbols. This is still saying A is a subset of B, but now it's possible that A is equal to B. Or not, it doesn't matter. Whereas in the previous case, A is a subset of B, but we're not allowed A to be the same as B. Yeah?
The second one should be the A sub B.
This one here? Yeah, this is...
No, the above.
This one? Yeah, we can still say A is a subset of B. We're saying that A can fit inside B. Everything that's in A is also in B.
But there is four.
I know. Subset only needs everything here to be also in here. But it doesn't... It can have extra. Do you know? So I could even have 4, 5, 6, 7, 8, 9, 10. No problem. As long as everything that's in A is also in B. But I think someone was asking me, I think you were, Dasha, it doesn't have to go the other way. It doesn't have to be everything in B is also in A. You know?
Can you show the whole picture?
Okay. Okay, that took a little bit longer than I would have thought. Is this okay now?
Yeah.
Here, I'll give you a little, for people who have written this down, a little interesting question. Well, if I say A is a subset of B like this, and B is a subset of A like this, there is only one relationship that could be true, so that both of these could be true. Yeah, they have to be the same. It's the only way that one is in the other, and the other one is in the first one. Don't worry about that. That was just not a trick question, a thinking question. Okay, we've actually talked about sets a little bit already when we did inequalities. So maybe just on the side as a quick revision, what is this symbol meaning? All real numbers. Real numbers, yeah. This one? Yes. No. Not integers. Oh, you're close. Rational. Rational numbers. This one? Nope. Integers. This one? Natural numbers.
Including zeros. Without zero.
Yeah, remember these? Now, what I want you to do as a small question is I want you to take these sets and write their relationship using subsets. So, which is a subset of which? They're all kind of nested together. So, do you know what I mean? Like, write out a line where you have something is a subset of something, and then that's a subset of something else. Think about it. It's not too difficult.
Just write down the examples to make all that.
Yeah. You have it? No, just like a list. Like A subset B, B subset C, C subset D. Yeah. Oh, it doesn't matter. Whatever you like. Start with the smallest and finish with the biggest. Yeah. Yeah, do you remember it? Include or not include? Oh, I thought you were telling me. Include. Yeah? Can I scroll down?
No.
Are you writing this down? Oh, come on, quicker, quicker. Okay, I need to scroll down now. This has been on the screen long enough. Okay, so what's the first set? N star, without zero. And that's a subset or a proper subset? It's a proper subset. Because the next set is definitely not the same, which is zero. Okay, what's the next one? Good. What's the next one? Good. And what's the last one? Yes. Now, let's look at these two. If n star is a proper subset of n0, that must mean there's something that's in n0 that's not in n star. What might that be?
0.
Yeah, 0 is in n0, and 0 is not in n star. If n0 is a subset of integers, that must mean there is a number which is in the integers, but that's not in n0. What might that be? Give me an example. Yeah, just give me one number. In the choice of infinite numbers you have, give me one number. Thank you. -1 is an integer. In fact, yes, fair enough. Is minus infinity in the integers?
Yes.
Is not.
Oh.
Right. Now, next one. If the integers are a proper subset of the rationals, that must mean there's a number which is in the rationals, but not in the integers. Give me an example. 1/2. 1/2 is rational, but 1/2 is definitely not integer. Right? The last one's a little bit tricky. If the rationals are a proper subset of the reals, that must mean there's a number which is a real number but is not a rational number. Pi is fine, yeah, and not infinity. Pi is a real number, but pi is not a rational number. Okay? And just to be clear, infinity is not a member of any of these sets. Okay, a little bit of notation that you already know. What is the meaning if I write this in sets? Union, yeah. So, yeah, and in probability theory it means or. In sets it means union. So what is the meaning of that if we were to write it out more formally? So let's just say if x is in A or x is in B, then that means x has to be in A union B. So if x is in one of them, then it has to be in the union. Okay? And likewise, if x is not in A nor B, then will it be in the union? No. Yeah. Yeah, it's okay? So basically, union just sticks the two sets together. And an element has to be in one of the original two for it to be in its union. I mean, this isn't maths. This is just, I have a class of students here, I have a class of students here. I put the two classes together to make one class. Students don't suddenly appear or disappear as the classes combine. Right. Next one. A intersect B. So, if x is in A and x is in B, then that means x is in the intersection. So in other words, the intersection is only the elements that are in both A and B originally. In other words, it is the shared elements. Okay? If x is in A and x is not in B, then is it in the intersection? No. What about if x is not in A and x is in B? It's not in the intersection. And I think you see where this is going. If x is not in A and x is not in B, then x is not in the intersection. Okay? So this is the definition, in a way, of the intersection. Okay? For it to be in the intersection, it has to be in both the originals. So, I'll give you an example of these. Yeah? Can I...
Is it like the P and Q thing?
Which P and Q thing is that now? Okay. Right, let's just practice here. If A equals ABC and B equals BCD, what is A union B? A, B, C, D. Yeah? And what is A intersect B? B, C. Yeah? Is that okay, guys? Can I scroll down? Yeah? Okay, what's the meaning of this? This is not A. So if x is in A, then that means x is not in not A. The next one's a little bit clearer. If x is not in A, then that means x is in not A. The complement of A. Basically, A complement means everything that's inside A is now outside, and everything outside is now inside. So, for example, I'll give you an example to help explain this. Let's say A is 1, 2, 3. The number 1 is in A, isn't it?
Yeah.
Okay. The number 2 is in A. The number 3 is in A. Okay, what about the number 4? Is that in A?
No.
No. It's outside, isn't it? So I could say 4 belongs to A complement. It's A complement is the space outside the set. If you want to think about it like that. So yeah, 0. Is 0 in A? No. So it's outside A. So it's in A's complement. Now the problem here is, what exactly are we saying is on the outside here? Can I scroll down a little bit? Yeah. So look, if I say A is 1, 2, 3, then what am I saying is not A? Well, that'd be 4, wouldn't it? It would be 5, it'd be 6, it'd be 0, maybe it's pi, maybe it's your lunch. Right? But is lunch inside A? No. So do you realize there's a small problem here? Yes, indeed. So look, there's a small problem here. The problem with not A is it can become immensely complicated if you're saying, okay, just include everything except the numbers 1, 2, 3, which means you're inside not A right now. So you need to define. I bet you didn't know you were inside not A, did you? So you need to define what is called the universal set. That is like the background set, the set of everything. Okay? So I'll give you an example. Suppose I say everything is all real numbers, U for universal. Then if A is the number 1, then what's not A? It's all real numbers except the number 1. Very good. Okay? If I say the universal set is, let's just say, the alphabet. Or, no, that's a little silly. The universal set is the empty set. No. No. Of all, that was the only example you could give that was impossible. Congratulations. Of the infinite number of examples, you picked the only one that doesn't work. Well done. Let's say the universal set is all the letters of the alphabet, or something like that. So if set A is A, E, I, O, U, then in this case, what would be not A? All the consonants, wouldn't it? B, C, D, etc. up to Z. Yeah? Okay. Are you okay with not now? Yeah. So, two more symbols to do. So A/B. Do we know what this one is? And I think you can pronounce it as A less B, if that helps. Less. Okay, you don't know this. Kind of like this, yeah. This means it's the set A, and then you remove everything that is shared with B. So, for example, if X belongs to A less B, then that means that X is in A, but it's not in B. Yeah, I'll give you an example. Watch. Here's A, B, C, D. That's A. And then B is B, C, D, E. So that's A, and that's B. A less B is everything in A, but you remove anything that it might share with B. So, what is the only thing in A that is not being shared? Just the letter A, isn't it? No, because what you do is you start with A and you delete whatever it shares with B. Okay, let's look at the other way around. B slash less A. So you start with B and you remove everything that it could share with A. What would leave you then?
E.
You remove B, yeah, it just leaves you with E, doesn't it? So you need to think of this as a bit like a delete. Okay? You start with A and then you remove what's shared with B. It's like a delete. Does that make sense for you? Yeah. Now you might have seen this before. I don't know if I remember showing you this. What does this mean? What's this mean? Yeah. Yeah, so what's this set? All real numbers except 0. Because you start with the real numbers and you remove the 0. You know? And what's this set? All natural numbers including 0, right? And if I do this?
Star.
Yeah. This is like the remove operation. Yeah. Okay. And maybe you know this symbol here. I was waiting for someone to say that so I could. Right, what's this meaning? Yeah, this is the size of set A. So for example, 1, 2, 3. What's that? Just 3 elements. So I guess if you had this set, 1, 1, 1, 1, what's that? 1.
What?
How many elements are in this set? 1. Right? Yeah. If I tell you to buy milk in the shop 4 times, because I think you might forget, you don't buy 4 milks, you buy 1 milk. Okay?
It's like a session like a class, a lot of people don't want you put the answers.
Say that again, which set?
In a class with a set of like scores. So let's say you got like 1.
Yeah, but you can't really use a set to represent scores because scores have an order. Each one is attached to a name. Sets have to be unordered. You only care if you're in or out of the set. You don't care about the order or anything like this. Yeah? Yeah? Yeah. This is all real numbers except 0. That's all it is. Yeah? Say this again. This one. Which part does it contradict? Oh yeah. 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 Let me write those down. Okay. So 1, 1, 1, 2, 2, 3. That's the same as 1, 2, 3. And the size of 1, 1, 1, 2, 2, 3 is the same as the size of 1, 2, 3. Is that what you're asking me?
No, I was trying to say
Shh,
that.
I can't hear him. Yeah?
I was trying to say that means that it can't be the same because of
These two?
yeah.
Oh, they're the same. They're the same. That equal is correct here. That's right. Believe it or not. Because in the first case, is 1 an element of this? Yeah. Is 2? Yeah, is 3? Yeah. Is there any more? No. Is 1 an element here? Is 2? Is 3? Is there any more? No. So they're the same. So I know they look different, but they are actually the same. Yeah? Yeah. So then the last thing that we look at is how you can represent these on diagrams. So you can represent sets by just using circles here. So for example, let's say A is the set, we'll go with 1, 2, 3, 4, and B is the set 3, 4, 5. Then you can represent this on what's called a Venn diagram. And I'll just make that a little bigger. Venn diagram here. And I also need to make what's called the universal set here. Let's say the universal set are the numbers 1 to 9. Okay, so this represents set A. This represents set B. And this represents the intersection. Let's start with the intersection. What elements are in both A and B? 3 and 4. What is in A, but not, yeah, okay, 1, 2. And then this one to finish it, 5. And then here, 6, 7, 8, 9. Okay, so you can just, I want to identify each part here. So this inner piece is A intersect B. What about both circles together? A union B. What about only this piece here? No, because B would include this. No. B less A. And this piece here? A less B. And what about on the outside? It's A union B. Yeah, complement, yeah. It's everything not in A and B. Yeah?
Why the numbers 3 and 4 in the middle should be A union B?
No, this is intersect. That's intersect.
Intersection
Only what's in common.
and the union.
Everything. And what about the whole diagram? What set is it?
Universal set.
Yeah, the universal set is the whole thing. Oh yeah, and sorry, I'll put in green. What about everything here that's outside A? Yeah. A prime, yeah. And B prime would be everything outside B, which is this. So, come on. Right, let's quickly write all the possibilities down. A union B, what would that be? 1, 2, 3, 4, 5. A intersect B? 3, 4. A less B? Just think, please, before you answer. 1, 2. B less A? 5. Not A?
5, 6, 7, 8, 9.
Not B?
1, 2, 6, 7, 8, 9.
Okay. 1, 2, 6, 7, 8, 9.
Ours is people trying to.
A union B not.
1, 2, 5,
No.
6, 7, 8.
6, 7, 8, 9.
Oh, union, yeah.
Size of A?
Size of A.
4. Size of B?
3.
3. Okay.
Size of union.
Okay. Yeah? All okay? Yeah?
Yeah.
I need to write down my numbers.
Yeah.
Can you repeat the F1 and the B?
With here? It just means not in A. So what's in A at the moment? 1, 2, 3, 4. So what's not in A?
The rest.
Yeah, the rest. That's all. 5, 6, 7, 8, 9.
Can we not find the number of sets, number of elements in the universal set?
Yes. Kind of. Yes. Now, let's have a just. Got that? Got that? Okay, I'll let you try these for a few minutes. I think it'd be good if you could do ABC in each question. Page 94, ABCs.
Practically, we just need to know, like, this diagram, like this.
ABC.
Yeah, practically.
Everything.
Yes?
Like that.
Yes?